this course, we will talk about 8 features of OSPF. Let's get started with OSPF root summarization. The basic function of network devices on data networks is to forward data packets from the source to the destination. The forwarding of data packets depends on the routing table for the entire network. As the network scale increases, the size of the routing table also grows larger and larger, consuming more and more network device memory resources, which in turn affects the performance of network devices. In addition, the larger the routing table size, the more complex the root query. Root summarization can address this problem. In this example topology, there are 3 routers, R1, R2, and R3. OSPF is configured on the network, and 3 areas are deployed. R3 is located in both Area 0 and Area 2, and is connected to 7 network segments in Area 2. R3 advertises information about the 7 network segments to Area 0 through Type 3 LSAs. Consequently, R1 and R2 calculate the routes to the 7 network segments through the Type 3 LSAs and add the routes to their routing tables. If R3 is connected to hundreds of network segments, routes of the corresponding number are added to the routing tables of R1 and R2, which consumes a large amount of memory resources. In this case, we can configure root summarization on R3 to prevent R3 from advertising specific routes of its connected network segments. After root summarization is configured on R3, R3 advertises only the summary route 192.168.0.0/21 to OSPF. In this case, R1 and R2 need to learn only this summary route and use this route to reach the 7 network segments connected to R3. This ensures network reachability and reduces the routing table size as well. Such route summarization applies to ABRs. If the ABR summary command is run on an ABR with the not advertised parameter specified, the ABR does not advertise the summary route or specific routes to OSPF. In this case, this command can be used to filter LSAs. The ABR summary command applies only to ABRs and take effect only on Type 3 LSAs generated by the ABRs. In this topology, the specific routes belong to Area 2 if route summarization is not configured on R3. R3 advertises these specific routes to Area 0 through Type 3 LSAs. R2 cannot be configured to summarize these specific routes and advertise them to Area 1. Route summarization can also be configured on ASBRs. In this topology, the specific routes to the 7 network segments are AS external routes. These routes are imported to OSPF using the import route command. By default, R3 advertises these specific routes to Area 0 through Type 5 LSAs. To summarize these external routes on R3, run the ASBR summary 192.168.0.0, 255.255.248.0 tag 100 command, in which 192.168.0.0 and 255.255.248.0 are the calculated IP address and mask of summary route, respectively. In addition, a tag is configured for the summary route and can be applied to routing policies. R3 floods the summary route to OSPF areas through a Type 5 LSA. Now, let's talk about our next OSPF feature, virtual link. Multiple areas can be created in an OSPF domain, and Area 0 must be configured as the backbone area. All non-backbone areas must be directly connected to the backbone area. All inter-area routes must be forwarded through Area 0, and the Type 3 LSAs can be generated only by ABRs. This topology shows an invalid scenario. Area 2 is not directly connected to Area 0. R3 is not an ABR, and it cannot advertise the routes in Area 2 to Area 1 through Type 3 LSAs. As a result, R4 cannot learn routes in Area 0 or Area 1, and nor can R1 and R2 learn routes in Area 2. The virtual link feature can solve the preceding problem. Virtual links are logical and are regarded as an extension of Area 0. They can be used to temporarily solve the problem of a non-backbone area not being directly connected to the backbone area. After a virtual link is set up between R2 and R3, R2 and R3 establish an OSPF neighbor relationship based on the virtual link. Consequently, R3 becomes an ABR and can access Area 0. To set up a virtual link between R2 and R3, enter the view of Area 1, run the vlink peer command on R2 and R3, and specify the router ID of the peer end. Then R2 and R3 flood Type 1 LSAs in Area 1. The Type 1 LSAs describe not only the router IDs of R2 and R3, but also the IP addresses and the costs of the interfaces connecting the two routers to Area 1. Therefore, R2 and R3 can use the Type 1 LSAs to calculate the IP address of the shortest path to each other and the IP address of the outbound interface. However, virtual links may cause a routing loop. In this topology, Area 0, 1, 2, and 3 are configured. A virtual link is set up between R1 and R3 and between R1 and R2. Consequently, R2 and R3 become ABRs. As an ABR, R3 floods a Type 3 LSA that describes routes in Area 3 to Area 1 and Area 2, and sends the Type 3 LSA to R1 through its connected virtual link. R1 then sends the Type 3 LSA to R2 through its connected virtual link. In this case, R2 learns the Type 3 LSA through Area 1, Area 2, and its connected virtual link. Because ABRs cannot use Type 3 LSAs that are learned from non-backbone areas, R2 can use only the Type 3 LSA sent by R1 through the virtual link. Therefore, the next hop of the route 3.3.3.0/24 calculated by R2 is R1, and the next hop of the route 3.3.3.0/24 calculated by R1 is R3. When R1 sends a data packet to R3, the data packet first reaches R2. R2 then forwards the packet to R1 through R4. As a result, a routing loop occurs. Now, let's talk about how to modify the priority of OSPF routes. The figure shows four routers. R2 runs OSPF, and R4 runs RIP. R1 and R3 run both OSPF and RIP. R2 is connected to the network segment 2.2.2.0/24 and advertises the external route to OSPF. R1 and R3 learn this route. Then R1 imports the route from OSPF to RIP and sends the route to R4, which forwards the route to R3. In this case, R3 receives the route 2.2.2.0/24 from both OSPF and RIP. If a router learns routes to the same destination from different routing protocols, the router compares the priorities of the routes. By default, the priority of RIP routes is 100, and the priority of OSPF external routes is 150. Therefore, R3 selects the RIP route. That is, R4 is the next hop of the path to the destination network segment of 2.2.2.0/24. However, this path is not an optimal one. To solve the problem, you can modify the priority of the OSPF external route on R3 to 90, so that R3 preferentially selects the OSPF route. Note that the priorities of all OSPF external routes received by R3 are changed to 90 after the modification. To prevent the priorities of other OSPF external routes received by R3 from being changed, you can configure a route policy, as shown on this slide. Now, let's talk about silent interfaces. In this topology, there is a router R1 and a layer 3 switch SW. The switch has 3 VLANs. OSPF runs between R1 and the SW to enable R1 to learn the network segment routes to VLAN 10 and VLAN 20 through OSPF. You need to perform the configurations shown on this slide on the SW. Such configurations activate OSPF on VLAN IF 10 and VLAN IF 20 interfaces of the SW. Then the two interfaces multicast OSPF hello packets, attempting to discover routers running OSPF in the two VLANs. However, the two interfaces are connected only to PCs. Therefore, the flooding of these hello packets not only is meaningless, but also causes extra burden on VLAN 10 and VLAN 20. How can we cope with this problem? In this case, we can configure VLAN IF10 and VLAN IF20 interfaces as silent interfaces so that they do not send or receive any OSPF hello packets. Consequently, the two interfaces do not establish OSPF neighbor relationships, but R1 can still learn the routes to the two interfaces. Next, let's talk about default route delivery. There are 4 scenarios for delivering the default route. In the first scenario, the default route is delivered to a common area. OSPF does not allow users to deliver the default route to OSPF areas using the import route command. In this case, you need to run the default route advertise command to deliver the default route. After this command takes effect, the ASBR delivers a Type 5 LSA to the common area. In the second scenario, the default route is delivered to a stub area. The ABR automatically delivers a Type 3 LSA to the stub area. In the third scenario, the default route is delivered to NSSA. The default route can be delivered to the NSSA by an ABR or ASBR. The differences between the two delivery modes will be described in detail later. In the fourth scenario, the default route is delivered to a totally NSSA. The ABR automatically delivers a Type 3 LSA to the totally NSSA. This topology shows a scenario where the default route is delivered to common areas. In a topology, 4 routers exist. R4 is connected to an external network. It is required that a summary route to the external network rather than specific routes be imported to OSPF. Before the default route advertise command is run in the OSPF view of R4, ensure that a non-OSPF default route 0.0.0.0/0 exists in the local routing table. When you run the default route advertise command, you can specify the cost parameter to configure a cost for the default route, or specify the type parameter to configure a cost type for the default route. After the command is run, R4 advertises the default route through a Type 5 LSA to OSPF areas. If no non-OSPF default route exists on R4, and the default route 0.0.0.0 needs to be advertised to OSPF areas through a Type 5 LSA, specify the always parameter in the default route advertise command so that R4 delivers the default route 0.0.0.0 to OSPF areas, regardless of whether a non-OSPF default route exists on R4. However, this parameter may cause a problem. If the link connected to R4 is faulty, R4 still delivers the default route to OSPF areas. Because R1, R2, and R3 cannot detect the link fault, packet loss occurs. In this topology, R1 and R2 are in an NSSA, and R1 is connected to an external network. If the neighbor relationship between R2 and R3 is in a full state, R2 automatically delivers a default route through a Type 7 LSA. If the neighbor relationship between R2 and R3 is not in a full state, the NSSA default route advertise command must be run on R2, and R2 must have a non-OSPF default route so that R2 delivers a default route through a Type 7 LSA to the NSSA. If the NSSA is changed to a totally NSSA, R2 automatically delivers a default route through a Type 3 LSA and a default route through a Type 7 LSA if R2 has neighbors in full state in the backbone area. The routers in the NSSA calculate the default route based on the Type 3 LSA. Now let's talk about how to filter OSPF LSAs. To configure interface serial 1/0/0 of R2 to filter the LSAs to be sent, run the OSPF filter LSA out command on the interface. If the all parameter is specified in the command, all LSAs to be sent are filtered. If the summary parameter is specified in the command, Type 3 LSAs to be sent are filtered. If the ASE parameter is specified in the command, Type 5 LSAs to be sent are filtered. If the NSSA parameter is specified in the command, Type 7 LSAs to be sent are filtered. You can also associate an ACL with the command to filter routes. To filter the Type 3 LSAs to be imported to Area 1, run the filter IP prefix 1 import command in Area 1. Only the routes that match the specified IP prefix list are imported to Area 1. After the configurations shown on this slide are performed, the Type 3 LSA of the route 192.168.12.0/24 is imported to Area 1, and the Type 3 LSA of the route 1.1.1.0/24 is filtered out. The configuration for filter the Type 3 LSAs to be sent out of Area 1 on R2 is similar to that on the previous slide, except that the import parameter is changed to the export parameter. Another method to filter Type 3 LSAs on an ABR is to run the ABR summary command with the not advertised parameter specified. If the filter policy import command is run on R2, the OSPF routes to be added to the routing table are filtered, but LSAs are not filtered. In this case, R3 can still learn the Type 1 LSA generated by R1 and calculate the route 1.1.1.0/24. That is, the filter policy import command run on R2 does not affect R3. R2 functions as an ABR and receives a Type 1 LSA from R1. According to the Type 1 LSA, R2 calculates the route, adds it to the routing table, and then generates a Type 3 LSA. If the commands shown on this slide are run on R2, this route is filtered out. Therefore, R2 does not generate a Type 3 LSA for this route, and R3 cannot learn the route 1.0.0.0/24. The filter policy export command is run on R1 to filter the external routes to be advertised. According to the configurations shown on this slide, 3 external routes are imported to OSPF, and route 192.168.3.0/24 is filtered out before being advertised. Now let's talk about OSPF packet authentication. If packet authentication is configured on the router that runs OSPF, the router writes some information in the packet header of the packets to be sent. Each OSPF packet header contains an AU type field. If the value of the AU type field is 0, no authentication is configured for the packet, and the authentication data field is empty. If the value of the AU type field is 1, simple authentication is configured for the packet, and the password is stored in the authentication data field in plain text, which is not secure. If the value of the AU type field is 2, ciphertext authentication is configured for the packet, and the password is stored in the authentication data field in ciphertext, which ensures higher security. First, let's talk about simple authentication on interfaces. This slide shows the plaintext authentication configurations on the interfaces connecting R1 and R2 to Area 0. The same password must be configured on R1 and R2 so that they can exchange OSPF packets. If another device is deployed on the link between R1 and R2, this device can easily obtain the password of the packets exchanged between R1 and R2, which is not secure. This slide shows configurations of MD5 authentication, one type of ciphertext authentication on OSPF interfaces. In the OSPF authentication mode MD5 Huawei command, 1 is the key ID and Huawei is the password. The key ID and password configurations of R1 and R2 must be the same so that they can exchange OSPF packets. With the ciphertext authentication, the password in the authentication data field is stored in ciphertext. Area authentication takes effect in an area. For example, to configure simple authentication in Area 0, run the authentication mode command in the view of Area 0 on all devices in Area 0. This slide shows simple authentication in the area. Note that the authentication mode and the password configurations of all interfaces connected to Area 0 must be the same. The configuration of ciphertext authentication in the area is similar to that of simple configuration in the area, except for authentication mode. You can also configure packet authentication on the virtual link. For example, to configure packet authentication on the virtual link between R2 and R3, run the vlink peer command and specify the authentication mode and password. When configuring packet authentication on the virtual link, pay attention to the following point. If area authentication is configured in Area 0, the same configuration must be performed for the virtual link because the virtual link is an extension of Area 0. Finally, let's talk about the OSPF multiprocess feature. When configuring OSPF, you need to set a process ID. The process ID is valid only locally. The process IDs on R1 and R2 can be different. Process IDs have significance only if multiple OSPF processes are created on one router. In this topology, 2 OSPF processes, 12 and 23, are configured on R2 to isolate OSPF routes. OSPF process 12 runs between R1 and R2. OSPF process 23 runs between R2 and R3. In this case, R2 learns routes from the 2 OSPF processes. R2 does not import the routes learned from R1 to process 23. nor imports the route learned from R3 to process 12. To import OSPF routes between the two processes, run the import route OSPF command. That's all for today. Thanks for listening.